Welcome to Statistic 1, Chapter 7, a normal distribution topic. Using the normal distribution as an approximation for the binomial distribution. From the previous video, we know that the normal distribution can apply to discrete situation. And we all know that the binomial distribution is a discrete random variable. So now we can also use the normal distribution as an approximation for the binomial distribution. So it does require some condition such as below. First of all, the number of sample must be large enough. Our number n must be large enough. If we have our number n which is really small, this discrete one, only some number like this, it's not really normal if we have something like it. But if we have something like we had a lot of number of n, a lot of them, so it's more likely to have a normal distribution. So in order to find whether n is big enough or not, we have this equation: n times p greater than 5, n times q greater than 5. And p and q are not too 1 or 0. Let me take an example. If n equal to 10 and q equal to 0.4, p equal to 0.6 because they are up to 1, so np equal to 6 and nq equal to 4. This one is not appropriate because nq is not greater than 5. If we have a larger sample and the same q and p, I have n equal to 200 and q. Here I have the same probability for p and q, so my new np equal to 120 and my nq equal to 18. Both of them are greater than 5. So in this case, we can use the normal distribution as an approximation for the binomial distribution. We know that the normal distribution can be represented in this form. Normal distribution, here is the mean, and here is the variance. For this case, how can we find the mean and the variance? The mean will be equal to n multiplied by p, and the variance equal to n multiplied by p multiplied by q. So we have a new way to represent this one. X, random variable x, has a normal distribution. This one means has a distribution. Here's a normal distribution of np and pq. Here is the mean and here is the variance. Moving into the example, we'll learn how to use a normal distribution as an approximation for binomial distribution. Let's take a look at the question. It is known that on average, 2 people in 5 in a certain country are overweight. A random sample of 400 people is chosen. Using a suitable approximation, find the probabilities that fewer than 165 people in a sample are overweight. First of all, we will find the probabilities of a person is overweight. P equal to 2 people in 5, so it will be 2 over 5 equal to 0.4. So now we will find the mean number of people who are overweight. 0.4 multiplied by 400 equal to 160. Now we find the variance, which is 400 multiplied by 0.4 multiplied by q, and q is equal to 1 minus p, so q equal to 0.6 equal to 96. Now we will look at the question. Using a suitable approximation, find the probability that fewer than 165 people in the sample is overweight. Because we are using an approximation for normal distribution, so we have to do something called continuity correction. Like what I said before in the chapter of modeling discrete situation, here are the wording. You have to really be careful with the wording here. Here they say fewer than. Now let me draw a graph to illustrate that. Looking at the continuity correction table, we will work out every single term in here. First, I want to talk about the words at most. When you have something at most, means that x is smaller than or equal to a. So I have the corrections here. Smaller than or equal to a. To make it correct, if I have something which is smaller than a plus 0.5, I can ensure that all my values will be smaller than or equal to a. If I have something from here, going from here, I can ensure that all my values will smaller than this one. The next one, at least, I will use another color. For at least mean that something greater than or equal to a. If I have my correction is x greater than a minus 0.5, so I can ensure all of my values here will be greater than or equal to a. If I have the word fewer than, mean I have value which is here smaller than a. So my correction is if my values is in this range smaller than a minus 0.5, it can ensure that all my value here is smaller than a. If value here, my correction is here, I1 is here, so the correction can ensure that all my value will be smaller than a. Moving to the next one, the words more than. More than mean that x greater than a, so it will be from here going up here. And my correction is x greater than a plus 0.5. If x is greater than a plus 0.5 here, it can ensure that all my values will be greater than a. And now, why the correction are important and you have to remember them? Because in exam, you will lose at least a mark or two if you don't know the correction. If you get one really big number like this, 165, and you might, because your result, you minus your mean here, will be from 0 to 2.9. Here's our z-score, so in the exam, they would never give it any other number which is not in this range. If this one is 2.23, I have a probability. I can use my z-score table to find the probability, but because this one is changed by 0.5 or greater than smaller, this one will change. It will result in something like 2.24, and it will result in another probability. So this one is the correct one, and this one is the wrong one, because we didn't use the correction. So please remember that you have to remember how to use correction. for special case. You have to be careful with the wording here. Now we will work out the rest of the question. Let's say, using a suitable approximation, find a property that less than 165 in the sample. So P less than 100 x greater than 165, so equal to P of my z score smaller than what I say here. My correction was minus 0.5, so here I have 164.5 minus the mean. Here's my mean, 160 over standard deviation, and it's either variance, so we take the square root of 96 equal to b of 0.4593, and using the table we can get our probability is 0.677. I rounded up because it is the final one's significant figure.